Actually, I would reshape the material again due to some other you can say other things. I just can't showcase directly the all material. I just had to reformulate it for the training. Okay, yeah, I think you can understand this.
Yes, sir.
Yeah, so these are the standard documents I'm having with. So we just will start with the training. So what CFD is, we as we understand from the this basics of this all sciences, it is used to for predicting the fluid flow, heat transfer, mass transfer, chemical reactions, and related phenomena. As we go on increasing number of physics inside that, the more number of calculations will be included, and it goes on. So basically we deal with the fluid flow, and in that we can add heat mass transfer, chemical reactions, and related phenomena, and we solve the basic equations such as conservation of mass, conservation of energy, then conservation of momentum, all these equations that comprises the Navier-Stokes equations. And yes, they the details are there. Some more brief is there on the coming slide. And what information we can get out of this is like distribution of pressure, velocity, temperatures, lift and drag. If you are dealing with the multiple phases, it is checking the interaction between the two phases, gas, liquid, gas, solid, and all that. Then species composition for the reaction, combustion, pollutants, and that kind of problems to deal with. We go with that, and many more to come. So this type of fluid behavior we can check at different stages, conceptual stage, at very initial stage, then detailed product development, optimization cases. If you are trying to troubleshoot any kind of problem that we are facing in the field regarding any of the products, and at any stage, we can just go with the CFD, and it complements the testing. It is not an alternative. It complements the testing. Also, we can say it is a virtual validation. Supportively, we will be conducting few experiments. So in that way, it can be used to better plan our experiments or testing cases. So this is a brief overview of CFD. And we know this is the very basic form of equation, Navier-Stokes form of equation, which comprises the terms of unsteady convection, diffusion, and source generation terms. So what Ansys has is like it has got CFX and Fluent solvers, and that those are based on the finite volume method, where we discretize this domain into finite volumes, and on which we solve this set of equations, where these partial differential equations are discretized into the system of algebraic equations, and those will be solved numerically. Again, we are briefing it is in a very short form what it does at the back end. So that was the a short overview of the problem. But how we should define the problem, how we should start the identification of the problem, is like defining the goal, like what we want to achieve, then domain identification. That's a computational domain, overall computational domain. Then it starts with the pre-processing, where we actually start with the tool and CAD model, then creating the mesh, then going with the physics and solver settings. Then comes the solving process. And for that solved case, we will do post processing, examine the result, check it with the test data, some standard papers, and decide on if it is matching, or we need to take decision that we have to again revisit to the first case, make some changes, and do the rerun, and prototype testing and manufacturing. These are the subsequent stages. So this is overall workflow. Any CFD workflow will comprise all these steps. Starting having some more idea about stepwise. So first step is defined as a modeling goals. So what we are looking for inside that, like pressure drop, mass flow rate, or say identification of maximum temperature inside domain at particular location, or some blind spot or for the flow. And those kind of goals should be in front of us, and then we will go with the next step of modeling options, such as the simplifications in terms of geometrical simplifications, then modeling simplification again will have broader aspects, such as whether we want to consider the symmetry, whether we want to use a very simplified model, or very say very high fidelity models, and what these kind of simplifying assumptions that we need to take care of, like that we need to consider at the initial stage, and their effect on the simulations. Next, it will be like simplifying the assumptions that one has to do. Again, the geometrical aspect and modeling aspect. Then the physical models that we will be considering based on the physics we are solving, the turbulence parameters, the energy transfer models. Then we can say any other special physics like species, multiphase, or moving mesh. Like based on the problem specifications, we have to decide on which models will be required to solve this problem. This is about the modeling aspect. Then comes the accuracy aspect, like what degree of accuracy is required. Now degree of accuracy will again be depending on the assumptions we are making and their effect on the calculation process. Say if there is some geometrical shape or some intricate shapes that we can't ignore, then we have to consider that shape. We can't just simplify it. Or there will be some minor holes in the systems for the say, nut and bolts assembly and all that, or some very fine or very smallest features which will not affect significantly on the flow and other gradients. Then in that case we can ignore those features, but without hampering the accuracy of the simulations. So this is about the geometrical aspect. Then comes the meshing aspect, where we consider very much, if we are not doing the mesh independent study, we will not get the idea about whether that is the very correct mesh we are dealing with, or the solution is independent of the mesh. So again, that part of accuracy will come. Then which type of models we are selecting, what are the limitations of that particular model. So all these parameters at every stage will add up, which will play important role while considering the accuracy. Next will be the time required for getting those results. If we go with a very coarse approach, simplified approach, and uh, say okay models, then you might get the results in very quick time, which will give you the fair idea of what is happening inside, or what is happening inside that computational domain to start with. So based on the requirement, we can choose the approach, and first simulations can be of very coarse nature. In the second case, we can just increase the fidelity. We can go to the low fidelity to the high fidelity option, and it will take more time but with more accuracy. So based on the need, we can play or consider decide this factor. Again, is CFD an appropriate tool? We can find whether we have any point solutions, or do we have any hand calculations or any parameters or anything available uh, which will give the results that we are thinking of. Like I want to check this through the simulations. That aspect need to be checked, because CFD analysis process is time consuming at each stages, and it takes times and very much efforts one's efforts to set up this case, analyze, interpret the results, check the accuracy, and uh, come to the conclusion. So that is very important aspect, whether this is an appropriate tool. By now considering all these aspects, we will go to the next step. Like we have now this defined modeling goals, and we all have assumptions and required accuracy and all that. Now we will go to the second step, named as identification of domain. Now you can see on the right hand side where there is a system of different pipes have been connected, and there is some component at the center, we can say cyclone separator or like that. And which part, like what is you based on the problem what we have specified or what we have defined. Now the challenge comes, where which what should be the extents of the domain, where should we cut off the domain. So now uh, the checks, or we can say the guidelines to consider the extents of the domain can be like this. Like boundary condition information at the boundaries, so we should be having where we are cutting this domain. Say on the bottom picture you can see the domain has been cut. Now the information should be available on these pages, on this sorry on this planes, where we are cutting this domain. Like we will be specifying some kind of input boundary conditions, inlet outlet or inlet boundary conditions, and that data it should be available. Like with the on the field there should be some gauges or some system which will give some uh, input data to us, and so that we accordingly we will cut our domains or we'll start the domains from that point. Again, the type of information available from the field data that can be accommodated in the fluent data. Like the information should be available in terms of velocity, pressure, or some flux data like mass flow data. If it is in the other form which will not, that cannot be accommodated, or that cannot be specified as some inlet, specified in terms of boundary conditions which are available in the Ansys tool. So that again we have to check. And if anything is not matching to this, we have to extend to the domain where this information is available. Until that point, we should be extending a domain. So the point here is like input conditions should be exact and they should be matching the field data. That is the idea here to define the or identify the domains. Again, the consideration of simplification such as 2D axisymmetric problem has to be there. And at this stage, again we have to consider that there are limitations. Every case can't be converted to directly just a 2D part, except just to check then effect what internally happens. But most 2D cases will not replicate the 3D nature of the problem. Hence there are limitations to the 2D, and again to the axisymmetric problem, whether we can go with that decision we have to make at this stage, and then we proceed to the next step. Then we go to the creation of a solid model of the domain. As a CFD engineer or CA engineer, in a CFD we deal with the volumes, and it is very much necessary to extract the fluid volumes out of the region. So initial part can be you will be provided with any solid model, or you have to create the volume out of with the dimensions given. So we can either make use of available CAD models and any other, or you have to just directly draw the sketch and then create the volume out of it. Again, in this case, the important step is like simplification of geometry. So there is an aspect like smaller features, fillets, bolts, and those can be again just simplified directly for compare it with that part and without that part. So how the solution is overall affecting, so that one can gain the confidence of defeaturing any parts inside the geometry. Again, here we have to consider if we are going with the symmetry option or periodicity option, then we don't need to go with the full-fledged model. We can just cut it down in uh, as per required, and we can go with the half model or quarter model of out of the full model. So those changes, necessary changes, has to be made inside this at this step. Again, since we need to apply some boundary conditions, any splitting, any so the boundary conditions or inlet boundary conditions faces should be very specific in nature. They should be independent, and if it is not there, then due to, with some geometrical modifications, we have to create them using geometrical operation, different geometrical operations. So here we extract the fluid volume, assign some boundary conditions, volumes, and all that, and then we go to the next step of meshing, where we discretize the domain. And again, here the critical aspects will be the mesh resolution around the key features, such as you can see on the right hand side. Uh, so this is the fluid volume, and this gray area is, we can say, cavity or solid model. Placing the sufficient number of boundary layers, placing sufficient number of elements inside this very fine gap is required to actually capture the physics around this region. So higher gradients will be observed during the analysis. So it has been taken care with a very fine or very fine mesh around this object. So this is required. Again, there are multiple examples we can see where the region is very much larger. Geometrical features are larger in dimensions. So the mesh will grow on that side. That is not an issue, but we have to take care of very smaller features. And while creating the mesh, we have to take care of the resources available, how many cells we will be dealing with, and what is the hardware capability available with, or how much time it takes to create that kind of mesh. Based on that, we will be creating the fine or coarser mesh or medium fine mesh, and what type of models we are using. Again, that will play the part. Like if it is a multi-phase analysis around some rotating equipment or some rotating event, so around that object, we are expecting some finer gradients of some solution. Yes, you are saying something.
Yes, sir. I was a bit like confused with the diagram. So, okay, sir, I understood it now.
Diagram?
The diagram, sir, I was confused like why there were like different colors. So, okay, I got it. It is due to the difference in meshes, I think.
It is not due to the meshes, but the different surfaces. it will highlight the different surfaces based on their projections or based on their the different components being listed inside the CAD model. Based on that, they will be separately highlighted as a solid model or as a surfaces also.
Okay, okay,
Okay.
okay. I got it. Got it.
So we now move to the solver step. Inside the solver, we assign different material properties, fluid, solid, mixture. We select the appropriate models, turbulent, combustion, multi-phase, which is as per the requirement of the problem. We have to go for the specific physical models, and then describing the boundary conditions, then giving the initial values, or as a previous solutions, any previous solution is available, we will just read that file if it is available, setting up the solver controls, and setting up the convergence pointer. So these are the few steps which we will do in the setup solver, and we will go to the compute this solution where uh, we will check for the convergence. And now, along with the convergence, I will just repeat these some important points, such as how the convergence will be checked, and their behavior or debugging also. So during the convergence, we have set up the case. Say we have some few assumptions, geometrical assumptions, some modeling assumptions, and now we have run the case. Now, how one will say that my solution is converged? So there are some criteria such as this residual graphs, where it will represent the variables such as continuity, x, y, z, momentum, and if energy we are solving, and any additional parameters the model we have selected. Those parameters will be shown, and the error in the system for those particular variables will be plotted in this graph with respect to iterations or time. Now, alongside this, like if it is showing very decreasing trend, okay, we understand solution is converging, the error is getting decreased, and at say 10 to minus 3 minus 4, it has shown that solution has converged. But this is not the single criteria we should be checking for. Other properties can be the solution variables, which we create as a solution monitors also, where so those should be created, and those should be monitored over the course of this calculation. Say if you get this very simple case where the flow through pipe is should be modeled, then in that case we can consider solution monitor or solution variable can be the delta p value inside that pipe. Or say if there are some uh, cooling or heating is expected out of that simulation where the flow will pipe, so we can consider what is the outlet temperature from that pipe. So these can be the multiple solution variables which will be create and which will monitor throughout the simulation. So if you consider delta p of the system, so we know that after some time, uh, for that particular inlet boundary condition, there is a fixed delta p which will be getting established for a fully developed flow. So the same condition also applies to the simulation case, where initially it will show some fluctuations, but after some time it should show a very fixed value of delta p, and that is what we will try to monitor. So uh, say there can be a time when the error in the system might be below 10 to minus 3, but that delta p is not established. So we have to continue that run to achieve that flatness or to get that constant value of delta p. So in that way, we can use those solution variables. So that is one thing. Next is overall property conservation, such as the mass balances, energy balance inside the system. We should check. Those should be having less than 1% of imbalance should be achieved. More the imbalance, more error in the system, and inaccurate results. That's what it means. And apart from that, if any other parameters of interest such as drag, pressure drop, as we discussed, we should be checking on that. So if all these points, residual imbalances and the solution variables are matching, or they are satisfying all our expectations, then we can say the solution has been converged for all set of given problem with the given assumptions and all these particular selections. So that's when we say the solution has been converged. Again, to judge the accuracy of this solution, we will check our accuracy of physical models or type of physical models we have selected, the assumptions we have made at every stage again, then the mesh resolution and independence. So one has to do create multiple meshes and check one of the variables how they are affecting with the mesh changes, and the numerical errors that will come with the different solution method selection and discretization schemes, and again with some models also. So based on this, we will say how much accurate this solution is. So this is again A very important step when we interpret the results or analyze the results and their nature. We monitor the progress. We'll see how one by one how this can be done in a better way, and what are the step-by-step processes or what are the checks, and ensure our solution is converged or accurate. The next step will be examining the results. Again, if one is satisfied that the results what I got is the solution has been converged, the particularly pressured data or whatever variables we are checking, they are matching with the with some proportion, with some agreements, with some agreement value, with the test data, some field data, or some standard literature data, then one can go to the uh, creating the doing the post processing in terms of visual post processing, or some numerical data extraction. So flow pattern, checking the flow patterns, checking the contours vectors of different variables, plotting the path lines and flow lines, getting some numerical values of forces and moments, anything that we can just create a report out of it and check. Now we have got everything. We have defined some problem with some set, some particular set of assumptions, and now we have also the results. Now we will check how it is closely matching. If it is not closely matching, why it is not matching, which assumptions can it might be it might be affecting. Say, is the flow turbulent, or whether we should be going switching from steady to unsteady. Is that approach required? Is there any compressibility effects needs to be considered? So those type of say brainstorming will be required at this stage to work on that problem. So in that case, we can just go back to the what is the actual physics that is being happening there in that particular computational domain. We can understand this from the very basic, very fundamental books, very fundamental research papers in that particular area. Also can take similar references from the numerical analysis of research papers. So from that we can understand if we are missing something from the modeling side. Then about the boundary conditions, what type of data we are getting from the field, and the same has been applied at the in the numerical models, the boundary conditions types and their values and their reasonability. So those aspects can be checked. And again, about the mesh resolution, mesh independence study, that we have to recheck all this. And once we do this, if we are satisfying, then we will go to the next steps, or this cycle will go on repeating, which we will do from we will make some changes and reiterate it, make some changes and reiterate it. So that is how this process will go on, and this is the standard procedure for any CFD solver that it will take care. Okay, so this is very initial overview of CFD. Just let me know if you have any questions on this or anything about the CFD, what we have covered right now.
No, sir, it is all fine for me. I understood it pretty much fine so far.
Okay, fine. So have you opened this space claim? It's
Yes,
like it is
yes,
a first time
yes.
thing. Okay,
No, no, no. I have seen like the space claim.
I will just give you the quick overview of the options placed over here. See, so now this space claim, if you just compare, as you said that you are more versed on the design modeler as compared to the space claim. Design modeler is a history-based tool where whatever operations we perform, those will be recorded, those will be say we can refer to that history what we have created. But here it is not, it is a direct modeler, and we can do local changes, and those local changes will be effectively applied very quickly. So if you go to just say we have performed 10 operations in the design modeler, and now you want to make some changes in the operation number two, which is now very eight operations late, or you can say eight operations behind recent. So it will take a lot of time to take that effect, because it is a feature based or say history based. But this is not the case here. A very direct modeling is possible, local modeling is possible, and it is more towards the we can say modification part. The capabilities there with full-fledged say CAD modeler, where say one can start with the sketches from the very beginning. One can start and create a very larger model, so there are no limitation from the sketches side, and it is very much comparable to the very market leaders in the CAD industry, such as Mini, NX, and all that. So the look wise and operation wise, it is very fast and direct modeling, and it is very much suitable for the CAD for CFD kind of operations, where we are interested in creating some extracting fluid volumes, checking for the geometric cleanup, and perform some name selections and share topology and all that. So that's the basic difference between the design modeler and SpaceClaim or any other CAD tool such as CATIA or NX and all that, where they are mostly feature-based tools. The modifications becomes very much simplified and quick with the such kind of a direct modeler, which is the SpaceClaim. Okay, coming back to the SpaceClaim overview graphic interface. So at the top we get different tabs. As their name suggests, they include sub options under them, such as Sketch tool will include all the sketching options, which comprises of the creation tool, modification, if you want to apply some constraint and editing and all that. So that will comprise the Sketcher tool. When we go to the next design tab, it will have some orientation related options for the object, then different modes, sketch mode, section mode, and 3D mode selection options. And then comes the mostly used tools such as edit tools, tool move fill combine, which is intersection tools, say we can say boolean operations that we call as using this split and combine tools. Then again, we can take references of some planes, axes, coordinate systems, points, pattern, shell, offset, mirror. Those options are available under the create tab, create sub option. And we can also apply some equations and some uh, predefined shapes, cylinders and sphere, which we can just directly specify the details and those will be created. And few options such as recording again, it will give you the exact feeling, or say the features such as the saving of history, whatever operations we are performing, that can be recorded in terms of blocks and script. So if you want to go back to the very older steps and just make few changes, some numerical changes, we can change the values and that particular operation will be edited. So that history can be retained or checked if we perform or if you go with this block operations. So these tabs are placed here. Then comes the display tab, where we go with the layers option, graphics, then we can say transparent and transparent view and all those options. Splitting of windows, those are available. Next, some assembly related. If we are dealing with this tab will be mostly one can use who is in the CAD modeling. Those that will be used here, like assemblies. We can say CAD models are being assembled, applied some constraints to match their orientation. So this tool is helpful for such operations. Yes, whatever we create, we can measure them through this major tab, where we can measure entities, mass properties, also inspect the geometries, using this tab. Also check for interfaces and qualities such as normals, surface normals, curvature, drafts, and the few other parameters with this major tab. Then there is a facets tab. This we can say one of the important tab when we are dealing with the STL file formats or faceted geometries. The faceted geometries are the geometries which will not have the single continuous surface, but very fine forms, or we can say elements, what we create as a mesh. So in a similar way, solid body will be single, but on the surface it will have multiple faces, and one has to combine all those surfaces in order to proceed to the volume extraction and do further operations. So those related options are available under the facets. Then comes the repair tab, geometry cleanup tab, which is very much helpful and which is required when we deal with a predefined or any existing CAD. We have to import here and check for different operations and check for the errors, remove them, so that one can create a watertight geometry. A very clean CAD can be created, and out of that we extract the volume, and which will reduce our efforts, or which will help to create a very good quality of mesh. If you go with the very bad quality of geometry, then it will increase our efforts to the meshing. So one should be very aware that if it is a bad CAD, one should take very much conscious efforts to make it clean and a good CAD, a watertight geometry, so that a good quality of mesh will be created. It is not the thing that there is no way that one proceeds with the bad CAD, bad geometry, and one can work around it in the meshing mode. It will take lot of effort. It is just waste of time to play with the bad CAD in the meshing mode, where the quality will not be maintained. And anyway, if you can get some mesh out of it, it will be very poor mesh, and it will result in the divergence or inaccurate results. So it is not advised to go with the very bad CAD model. Bad CAD model, what is that? We will just see. But it is advised to spend and work on the bad CAD model. At the save the efforts in the meshing, and the good mesh will be created in a lesser time. So that those options are related, those related options are covered in the repair tab. Inside the prepare, we create volume extraction, mid surface extractions, and all that. We check the interferences, rounds and faces and short edges. We detect some bad faces through this prepare tab. So we are extracting the volume out of this, and then we will go to the next sessions or next steps. Then we go to the workbench tab, where we again have some say multi-physics options available, such as IcePack related entities can be created here. And this is again suitable for the IcePack, the users who use IcePack, which is an electronics cooling software under the Ansys. Then under the workbench, the very important tab comes up, like shared topology, why that is required, and their significance and alternatives we will discuss. But that options are available under those options are available under the workbench. And from this tab also we can switch to the Fluent measure, or what we call it as a single window workflow, and that can be that we from here we will switch to the Fluent measure and proceed further. So those options are available here. Now, there is a SpaceClaim meshing available, which is the block meshing. So those options are shown here. Uh, it is very much similar to the ICM CFD meshing, and from that the hex meshing can be achieved using this SpaceClaim meshing, and that is shown here under the mesh tab. Then comes the detailing part, where one can do the drafting or create the annotations, such as the name, the dimensions of the system inside that particular systems. One can create using this annotation tab, and which are again very much they can be used in the reports when create the reports. Hence, it is not just required that one will be showing this. This is my computational domain. This looks neat from this X side, Y side, but one has to again add the details of dimensions to that. And SpaceClaim will give you the 3D view, the wireframe view, whatever suits you. You can use them, and in that view, one can create the annotations, dimensions, and put it inside the reports. Then there are some additional sections such as sheet metal part, some additional tools, and all that. So this all comprises the what we call as a ribbon tab inside the SpaceClaim. Left hand side, it is covered with the structural part, where whatever CAD models we create, then that can be volume entity, that can be surface entity, edges, points. Those all will be listed inside this left hand side structural structures tab. Next is layers, used for the layers modeling, the CAD modelers who are using this type. So those do. Next is like power selections. Say it is again useful feature when we are dealing with the CAD modeling or handling CAD model in the SpaceClaim. So there will be multiple edges, faces, surfaces, and say volumes of different dimensions. And to identify them, one just has to select those faces, and it will show multiple options. Like if you just select one of the edges with the length of 5 mm, it will ask, should I consider all the edges inside this domain for the which length whose length is around 5 mm. So those multiple options around that selections will be shown, and so that can be used for the multi selection, or you can say power selection, which will help or which will be very convenient to select for selection. So that is the selection tab available. Groups, here we create name selections to identify the particular surfaces as boundary conditions, walls, or symmetry, or any other post-processing entities that we are interested in at the post-processing stage. So those will be highlighted or specified uh, under this tab. One has to come here and select those surfaces and create those name selection. That is NS that has been highlighted. In the design modeler, it is name selections. Here, at times, the short form is also used as a NS. And next is parameter. If you want to if you are interested in creating parameters, geometrical parameters, and those will be again created from this groups tab. We will see how this can be done. And there is a view tab, preset views, which we just can, these are the shortcuts available, and also we can go to the particular options. It will switch to the views. Besides that, there is options called as selections, and whatever we can say, whatever entities we are selecting or whatever operations we are selecting, related to that, few details will be placed under this options tab, and those options will be seen here. And under that, under this options tab, there is a property tab shown. Property tab very rarely used. Few property details will be shown here, highlighted here. Then we have at the bottom the status bar, which will show how many windows are open here, design, how many in which how many components have been opened here. Some selections that we make, those will be listed here. If you create any surfaces, it will show one face has been selected, one edge has been selected, one volume. So those kind of information will be plotted, and some selection shortcuts like pan, zoom, then those options are available. Undo, redo, those options are available under the bottom, which will be not used frequently. One can just go with the fingers and mouse related operations. Uh, in addition to this, here we can do undo redo, which is again a very peculiar feature of the SpaceClaim as compared to the design modeler. In the design modeler, we can't use the undo redo tab. It is available with, say, what I remember is for up to 50 operations going back. It can go up to 50 operations back by doing undo and all that. So that is also helpful tool. But the thing here is, whatever you create, just don't save as a history. So now if you are working on a larger models, the tip will be just save the models in a step-by-step way. Say if you're working on a CAD model for 3 days, so at least you should be saving a CAD model in a day 2 times. So that you are creating backup, so that it will record that particular operations have been created up to this time. And if you want to go back, if you are performing continuous operations, and if you feel that I need to go to the previous step, what I was doing in 2 days back, so in that case you will not have access unless and until you have created a special backup file. Otherwise you have to start from scratch again. So that is also one of the uh, say disadvantage of this direct modeling, where in the design modeler kind of a software or feature based software, you just have to delete those particular operations or hide that, so that you reach to that particular stage, which is not possible here. Alternative to this can be creating backups at the regular intervals, which will save over time. So that can be one of the uh, advice over here.